What separates a Porsche Flat 6 from a Toyota Avalon V6 aside from the bank angle, the power output, the engine location, and your interest in owning one? At full throttle, the Porsche belts out an aggressive mechanical rasp while the Avalon mutters a non-threatening burr. How can two six-cylinder engines sound so different? Before we answer that, a brief primer on sound. It originates as vibrations that cause air pressure disturbances that hit our eardrums. The frequency, or hertz, of a sound wave, how many times the wave oscillates in a second, determines how our brain processes and interprets it as a distinct pitch. A higher frequency makes for a higher pitch, and vice versa. A car's engine under load plays a range of frequencies, but its root note, the pitch its musical chord is built on, is defined by its so-called dominant frequency. These sound-generating vibrations derive from the combustion in each cylinder and the corresponding pressure waves in the intake and exhaust systems. They are all keyed to the engine's rotational speed. As revs rise and fall, the pitch goes up and down. Calculating that dominant frequency at any given RPM is straightforward. First, you convert engine RPM to Hertz, the frequency unit, with the following formula: 60 RPM equals 1 revolution per second, or 1 Hertz. Thus, a V6 spinning at 1800 RPM can be said to be running at 30 Hz, 1800/60 equals 30. But because a 4-stroke engine fires each cylinder only once every 2 crank revolutions, we're only worried about half the engine's cylinders. Multiply our 30 Hz value by 3, the number of ignition events per crankshaft revolution for a 6-cylinder engine, and you have the 90 Hz dominant frequency that defines the 6-cylinder's sound at 1800 RPM. As the engine speed increases, the firing frequency rises proportionally. In a 6-cylinder, it's also called the third engine order because the frequency is 3 times that of the engine's rotation. In an 8-cylinder engine, the firing frequency is the 4th engine order. In a V10, it's the 5th. But that third order frequency is just one component of a 6-cylinder's timbre, which is a fancy term for its distinctive sound character. Even if a flat 6 generates the same dominant third order frequency as a V6, our Porsche and our Toyota can still sound very different. The engine's overall timbre is a matter of thousands of variables, as the firing frequency excites additional vibrations in the structure and plumbing. Most throaty, aggressive-sounding cars have very high half orders, such as 2.5 and 3.5 times the firing frequency. These produce the growl that's desirable in a sports car. They are normally adjusted through exhaust tuning. The relative loudness of the higher orders defines these two engines' distinct timbres. They are the pitches that build on the root note to create the engine's distinctive chord. Which ancillary frequencies are allowed to sing and which are muted is the work of the noise, vibration, and harshness, NVH, engineer. An exhaust muffler cancels some unpleasant frequencies that otherwise might resonate in the cabin at a certain load and RPM. Every engine's sound is the product of a whole orchestra of bushings, pipe diameters, and hundreds of sheet metal pieces of varying thicknesses, as well as design factors, such as the exhaust layout, insulation, and the body shell. Each cylinder produces a bang, and the way the engine is shaped, the firing order, and the exhaust manifold layout control the way the bangs mix together, says Matt Maunder, a powertrain noise and vibration specialist at Ricardo. Consider two loud and proud 8 cylinders that sound nothing alike. The firing order of the Ferrari 458 Italia's flat plane, 180-degree, crank V8 alternates between cylinder banks, making for a silken, sonorous sound. In contrast, the Chevy Corvette small block V8 emits a lumpy burble due to its cross-plane, 90-degree, crank and a firing order that produces irregularly spaced pulses from each cylinder bank. So why does a Toyota V6 sound different from a Porsche Flat 6? For the same reason that nobody ever goes to the Met to hear Motley Crue. The colors of the wind. These fast Fourier transform, FFT, plots, produced for us by the NVH experts at Sound Answers, show the frequencies recorded at the respective car's tailpipes during a run through the gears. The color indicates the loudness in decibels. Yellow is the loudest, indicative of the dominant frequencies, while the vertical axis shows the frequencies. A higher frequency creates a higher pitch. How to make 6 sound like 8? Electronic sound enhancement, also known as that thing you really hate about the newest BMW M cars, uses the cabin speakers or an electromagnetic shaker attached to the firewall to generate its own internal combustion soundtrack. Knowing only the engine RPM and load, it's possible to completely alter the perceived engine timbre. If you want a 6-cylinder engine to sound like a V8, at 1800 RPM you generate 120 Hz and multiples of that fourth-order frequency, rather than the 6-cylinder's natural third-order frequency of 90 Hz. Artificial enhancement may be taboo among purists, but it's increasingly popular among automakers because it's cheap, effective, and adds minimal weight. As far as the feds are concerned, passenger cars and light-duty trucks can be as loud as automakers dare build them. However, engineers treat the pass-by noise regulations set by various states, counties, and cities as national guidelines to simplify manufacturing and sales logistics. The loudness limits range from 80 to 96 dBA and sometimes higher depending on the locality and the type of vehicle. The test procedure is defined by SAE standard J986, which calls for the vehicle to accelerate at full throttle from an initial speed of 30 miles per hour in second or third gear up to redline.